Okay, let's get started, everyone. So this is the last class of the semester. Today we will be talking about some very new developments in the field of language models, NLP, specifically alternate architectures to the transformers that we've focused on for the vast majority of the semester. So before I start on that, just wanted to reiterate that you have a quiz that is due, well, I think Friday, and you also have your final project reports. Please use the template that we have provided for your final project reports. It has a list of all the sections that you need to complete. We expect you to follow that template for the most part, and if you want to add additional sections, that's fine, but do make sure to include every single thing that we have requested in that template. So there will be a grade scope entry for your final reports shortly. As far as your code, we would like you to email your code to the instructor's account, like one member of your team, CC all of the other members, and email it to the instructor's account. Ideally with a README that tells us, exactly what we should do if in the case we want to run your code. Obviously, if you are relying on very large models or data sets, do not include those as part of your code, but do mention like what you need, external dependencies to run it. Okay, any questions before I start with the topic? All right, so I looked at some of your requests for what to talk about today, and a couple of you mentioned you would like to talk about new architectures, things that are beyond the transformer. However, today we're going to actually talk about something that we discussed towards the beginning of the class, the recurrent neural network. But it has kind of made a resurgence recently in all of these models that we're seeing that are competitors to the transformer, like Mamba and Griffin and so on. They're basically taking ideas from recurrent neural networks, but modernizing them such that we can train in parallel now instead of in sequence, and also perhaps combine these recurrent blocks with local self-attention blocks like we have in the transformer. So let us start then with just an overview now of some of the issues with transformers. So we know that transformers have been around for 6 or 7 years now, and there hasn't really been any architecture that has been proposed that has supplanted the transformer, right? We're still all using transformers today. All of the models that you might be using in your projects, like Llama 3, for instance, these are all just transformer models. Some parts of the transformer have changed, like perhaps the order of the components within a block, but by and large, it's still the same thing that was released in 2017. So what are some advantages of the transformer? We know that it has a powerful memory, right? Its memory is not bottlenecked into one vector, right, as it is in a recurrent neural network, but we can access specific parts of the input via the KB, the keys and values that we have for the rest of the prefix, right? So while a recurrent neural network has just a single hidden state that represents all of the information in the prefix, a transformer allows us to easily look up parts of the prefix that might be relevant and put them into the hidden state. So it has a very powerful memory. We know also that one big advantage of the transformer is that we can parallelize it. God, this will be the last time I write this word for a year. Parallelize during training. right? And we discussed how a recurrent neural network cannot be similarly parallelized. We have to compute it in sequence. We will revisit that today, though. Another problem with the transformer is that it's slow at test time. So we have to do all these query key dot products and value vector weighted averaging across multiple blocks before we are able to compute the distribution of the next word. Recurrent neural network is much faster because you have just this memory for everything that you've seen in the past, and all you need to do is one update, possibly a deep update, but still you just have one vector and you need to kind of add information about the current word into that vector. So it's much faster at test time. Okay, so some issues with RNNs, right? That unlike the transformer, it has this memory bottleneck. So especially for longer sequences, we are kind of just shoving all of the information that is relevant into a single fixed dimensionality vector. And it might be very difficult to represent long and complicated sequences in this way. It might also be difficult to pick and choose information from well in the past if it's not well represented in that context. Unfortunately, it is also not parallelizable. All right. At training time. And this is the fundamental reason why the transformer was invented, right? Because RNNs were too computationally expensive to scale during training to very deep networks and large numbers of parameters to a lot of data. However, they are fast at test time. So we have these kind of three different aspects of these two networks, where over here we have a recurrent neural network whose memory is not very expressive, but it's faster at test time, and the transformer is computationally fast at training time compared to an RNN, but it struggles with the test time, and also it has the quadratic complexity on the sequence length, right? So let me add that here. In the sequence length L, right? Whereas the recurrent neural network, you are not computing these query key dot products over the entire sequence, so it is not quadratically scaling in terms of the sequence length. So this is kind of where we are. And a large reason that we might want to move on from the transformer is because of this quadratic complexity, right? As we scale up to longer and longer sequences, we've currently made a lot of advances using things like flash attention and ring attention, but we're going to be limited in how long these sequences can get. And that might be especially relevant in domains such as video, where the inputs can get very, very long quickly. Also, for example, if you want to train over millions or hundreds of millions of tokens, it could become difficult. Okay, so RNNs, in contrast, they just haven't been very well studied since the transformer came out, but recently that has started to change. So I'm going to spend most of this lecture talking about a variant of recurrent neural networks called the, just a linear recurrent neural network. So it doesn't have any nonlinearity associated with it. It turns out that you can actually, if you have a linear recurrent neural network, compute all of the hidden states in parallel, which is a very interesting property. However, that means that our recurrent neural network is not going to be very expressive, right? It can't compute these nonlinear transformations. But as we'll see, we can put these nonlinearities elsewhere in the network. So what happens if you have a linear recurrent layer followed by a nonlinear feed-forward layer. Now, potentially, you can do both of these computations in parallel and kind of get advantages from the nonlinearity, even though it's not directly applied to the recurrent step. So that's kind of the fundamental idea underlying all of these new like transformer competitor networks that have been released over the last year. So let's take a look first at our standard RNN equation. Right, so H sub T equals F of, and we called it WH, HT minus 1 plus WE CT. Right, so this part is responsible for the hidden state transition, and this part is responsible for the current input token. Now, a linear RNN is literally just the same thing except without the nonlinearity. So we have WH HT minus 1 plus WECT. And as I said before, no non-linearities here means lower expressivity. So we might not be able to model complicated phenomenon like negations and things like that with this kind of linear recurrent neural network. However, what happens if we put a nonlinear feed-forward layer on top? So this is the interesting question here. So currently we have H sub T here as just this linear, we're adding these two matrix vector products. But what if we have another, and actually here, let me change the terminology a bit so that if you are reading the Mamba paper or any of these state space model papers, you can directly map what we're talking about here to those papers. So maybe I'll do this in red here. In all of this literature on state space models, they use the matrices A for the hidden state transition and B for the input. So we're just going to use that for the rest of the lecture too. But these correspond directly to the W sub H and W sub E that we've talked about whenever we discussed recurrent neural networks earlier this semester. Okay, so given this, one thing we can do is compute, let's say, put a feed-forward layer on top. So we have F of, let's say, matrix C, H sub T plus D, and then the current input. So now H sub T is the only part of this that deals with the previous hidden state, right? Assuming we've computed H sub T, this part can be applied in parallel across the sequence, right? There's just a feed-forward layer. It has no dependencies on the previous time step. And now maybe Z sub T is fed into the next layer of this, model, which consists right now of a linear recurrent layer and a nonlinear feed-forward layer. Just like in transformers, we have our self-attention, we concatenate all of the multi-head representations together and pass them through a feed-forward layer. Here we have a recurrent linear layer and then a nonlinear feed-forward layer. Does that make sense? Any questions about this? Okay, so you might be thinking, well, the linear aspect of this is concerned with the transitions between tokens, right? So just because we put this nonlinearity on top, does it mean that this model can actually handle nonlinear relationships between the tokens in the sequence. And it turns out there are many empirical results that show that, yes, indeed, if you have a sufficiently deep enough network that's designed in this way, and with more clever formulations of this linear recurrent step. So Mamba basically has more clever ways of getting these B and C matrices such that they are not fixed across all time steps, but rather depend on the input. But with all these changes, you get a very, very expressive model that is capable of competing with transformers on many language-based benchmarks, as well as other like synthetic toy-based benchmarks. But I haven't told you yet how we can even parallelize this recurrent layer, right? All of this performance depends on the fact that we can train this very efficiently, because otherwise, why would we do this, right? We would just stick with the transformer. We know we can easily parallelize the self-attention computations. So first, let me just summarize this high-level idea, which is, again, critical to all of these papers on alternate architectures. All non-linearities, like this F here, are above the linear recurrent layer. So it's a very simple idea, but actually had not been explored too much before the introduction of transformers. Before transformers came about, we weren't really so interested in scaling up to this level that we see today in 2024. We didn't really have a need to parallelize these computations. All of the libraries prior to transformers were doing recurrent steps in sequence. So it was slow, but at that time we had much smaller models and smaller data sets, so it was still feasible. So there wasn't really any need to explore architectures like this, which, if you just look at it, they seem clearly worse, right? The transition dynamics here are modeled in a linear fashion, and if you could add a nonlinearity, why wouldn't you just do that, right? But as we'll see, there are big advantages to doing this. Okay, so let's go back to our favorite example. It's fitting for the last day of class. We've seen this so many times before. Students opened there. So again, we have some word embeddings here, C1, C2, C3, and let's say we have some hidden state, H sub 0, we have H sub 1, H2, H3, and so all of these transitions are handled by the B matrix, all of these are handled by the A matrix, right? So let's just for simplicity assume that this H sub 0 here is just a 0 vector, so it doesn't affect the first time step. Now, in our linear recurrent network, the computation of H sub 1 is just B times C1, right? We're just going to ignore H sub 0. And H sub 2 is AH1 plus BC2, and H sub 3 equals AH2 plus BC3, right? So we'll just unroll, write out the equations for these three time steps. Now, let's actually look at the computations if you unroll like this H sub 1 and this H sub 2 and write out all of the different terms in this, this equation. So let's take a look at H2 here. So H2 equals AB C1 plus BC2. We've just substituted H1 for what we computed up here. And H3 equals A squared BC1 plus ABC2 plus BC3. So similarly, we can write out, you know, H4 equals A cubed BC1 plus A squared BC2 plus on and on, right? And eventually, we can come up with this general formula, which is that the hidden state at any time step t is the sum, right? We see the sum of different terms here. So let's set this to the A matrix. We take it to some power k, and then multiply it by this B matrix, and I guess we have this CT minus k here. So essentially, the linearity of this recurrence allows us to express the hidden state as simply the sum of a product where one of the matrices is, one of the elements of the product is this A matrix taken to some power, right? And then we have the B matrix and the input. So maybe as a question to make sure you're following along, can we do the same thing with a nonlinear recurrent neural network? And why not? Yeah, exactly. So when you have the nonlinearity, you can no longer like decompose into this power formulation, right? Because the nonlinearity is changing. It includes both the previous hidden state and the current input, and there's just no way to do it unless you're doing all the computations in sequence. However, just because we have this, it's still a little unclear how we can do this in parallel, right? Now we have this equation, but it looks kind of like a cumulative sum of these products. How can we parallelize that? And so that's kind of the big implementation trick with all of these papers. The new papers is that there are several techniques you can think of to doing this kind of computation in parallel. So one, which is probably the easiest to understand, is what if we just look at this as a convolution? So we saw with computer vision models the idea of having this matrix that we slide across the window of these different pixels, right? So you can think about sliding different matrices across the sequence of token embeddings to accomplish pretty much the same thing. If you look at this equation, we might have different matrices here, like, okay, let me write this out. So how do we parallelize this? So we could treat this as a convolution and design our kernel, or we called it like filter or whatever, to include these matrices, right? It might be B, A squared, B, blah, 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 until some window size. And now we have all of these matrices. We can slide them over our token sequence and compute all of these hidden states using this method. Slide over sequence. So note that this does not allow us to compute all of the hidden states for the whole sequence in parallel, because that would require us to have like a length L size, like L different matrices basically that we're sliding across the sequence. In general, we're going to treat the sequence as a bunch of chunks and have a pretty small number of these matrices that we're sliding across, and then kind of aggregating the results. So that is one way to do it. But the way that the modern methods like Mamba and Griffin are implementing this is using something called a parallel scan. So that's what we're going to focus on for the next bit of the lecture. So in modern papers, we're going to look at this concept of a parallel associative scan. And the idea here is that we're basically going to break up the computations of this hidden state into smaller computations that can be parallelized across different processors in the GPU. And we'll do an aggregation over that with some sort of clever tricks to minimize the amount of compute that we're using. So eventually, the result of this operation will allow us to parallelize this hidden state computation without going sequentially h sub t plus 1, h sub t plus 2, and so on. Okay, so I guess maybe we can just do a simple example first, and then I'll come back to this hidden state, the linear recurrent network hidden state that we have been discussing before. So let's consider the simple case of the cumulative sum, which is very relevant for our hidden state computation. As you can see, this is also a sum of some terms. So how are we going to implement this with parallel scan? So let's make it a little more concrete. Here, we're just saying that the current element of this vector is a sum of all of the previous terms as well as the current term. So we're going to have some function. We're just going to deal with scalars for this example. Y at the position k is a sum of all the elements from 1 to k of the input sequences. So if I had this sequence, let's say 3, 1, 7, 0, 4, 1, 6, 3, then my ideal outcome here would be 3, 4, 11, 11, 15, 16, 22, 25, right? So that's our goal. So one way to do this is sequential, right? Just like in the recurrent update, I can just have this simple update y sub t equals x sub t plus y of t minus 1, right? This looks a lot like the recurrent update. But we would like to reduce the number of steps that we're doing on any one processor and try and parallelize it so that we can do a lot of this work in parallel and save overall compute. So that's where we get this idea of the scan. And this algorithm was originally proposed, I think, in like 1990, and this demonstration was shown with the parallel scan then. In 2018, I think, yeah, 2018, there was a paper that showed how this concept can be used to parallelize the linear recurrent neural network. Of course, no one really cared about that result in 2018 because we had transformers, everyone was using that. But this result has now become very relevant in the context of these newer models, where now we do have this linear recurrent type layer and we want to parallelize it. So it's cool to see how the technology has kind of, you know, in 2018, someone wrote a paper on parallelizing linear recurrent neural networks using these scans, and only 6 years later did it become like a very, very important concept. Anyway, let's take a look at our cumulative sum operation first, and then move from there. So I'm going to write out the sequence again, and basically this process involves considering the computations as a tree of intermediate computations, and you know, a lot of this might remind you of, you know, various dynamic programming things that you might have learned in the past. All right, so this is my sequence. I want to get this purple output as a result. So the first thing I'm going to do is sum all of the pairs in the sequence in a non-overlapping fashion. So I will have 4, 7, 5, and 9. And now I'm going to do another layer of this tree. So I get 11 and 14. And then I'm going to sum all of them to get 25. So if you look at these values here, they're not exactly what I would want, right? Going back to the cumulative sum, like clearly there are some parts of this tree that could be useful in recovering the cumulative sum, but I don't have it right now. I just have some intermediate values, and I do have the sum of the whole sequence at the root node of this tree. So this is considered the upsweep or reduce part of this, this scan. The critical part is the downsweep. So maybe I'll write that in a different color. So in the downsweep, we do the following. The left child gets the value of the root. So we'll just copy the value of the root. Oh, I should start, sorry. Let me just put this down a little bit. Okay, so the root starts at 0. The left child gets the value of the root. The right child gets the sum of the root plus the upsweep value of the left child. So this upsweep thing refers to the value of a node computed during this upsweep. Okay, any questions about anything so far? Sorry, I've been going pretty fast. Are people generally understanding why we are interested in parallelizing these linear recurrent layers? Okay, let me check on YouTube also. I've been ignoring that. Okay, I assume things are working on YouTube. Maybe I'll refresh just to make sure. Okay. All right, so let's go back here. And let's look at how this actually ends up working with our example. So I told you that the root node gets assigned a value of 0 on this downsweep. And now if we're going to, and the downsweep is going top down. So we're going to reconstruct this tree. The left child will get the same value as the root. The right child gets a value of the root plus the value of the upsweep of the left child here. So I'm going to be going back and forth a lot, I guess. But this child here will get a value of 11. And now we're going to just expand the next layer here. So you can see that through this expansion process, the first value here is just going to be 0, right? And we'll see why that makes sense in a second. But now here, we need to get the value of the left child for this, which is this value here in the upsweep. So we set this to 4. And finally, we can expand this to the value of the left child here, which is 3. And we've completed at least this leftmost path of the tree. Now let's go here to this 4, which is the first time that our node is not valued at 0, our parent node, and go down. So we know the left child here gets the same value as the root, so 4. And our right child gets 4 plus 7, right? The upsweep value that is associated with the left child. So, oh, sorry, I should have added these two. So now we've completed this part of the tree, and let us start with this side here. So the left child here I know will be 11, and the right child will be 11 plus 5. So 16. And now we know the left child here is 11. The right child is 11 plus 4, so 15. And similarly here we go to 16, and here we get 16 plus 6 is 22. So if you look at the leaves of this tree and compare it to our goal, which, there we go, over here. So, whoops. So we basically got what we wanted shifted over 1, right? So you can see how we did not compute this, the leaves of this tree here in sequence. We computed it instead in bottom up and top down, 2 passes on this tree structure, but yet we were able to get the same output. So now, if you think about it, why would we ever want to do this? Any ideas? What benefits could this this way of computing the cumulative sum offer us compared to the sequential version? Yeah. So let's look at this upsweep, right? I can do this, this all at the same time, right? There's no dependencies on the previous, there's no dependency here, right? This doesn't exist. So if I had 4 different processors, I could do this all, this whole level at once. And then the next level, I can similarly parallelize across different processors, right? And the same thing with the down sweep as well. So while the sequential version, I have to wait until I've computed the previous sum before I can get the current step sum. In this case, although it is kind of weird how we're doing this, it does allow us to parallelize these operations in the subtrees across different processors. And we know, like, when we're dealing with GPUs, that's kind of our goal, right, is to parallelize as much of the computations as possible. Okay, but this is great, but it's also not a linear recurrent network, right? It's just a scalar sum. So how can we actually generalize this to compute what we want? Yeah, you have a question. Yeah. So we could potentially use those if we had a different function that we wanted to compute. This is just the one that we would use for the cumulative sum. Yeah, so the idea is basically to do these, this upsweep and downsweep with a function that you define as, and there are some properties of this function that have to be satisfied. Like, I think the operation needs to be associative, and yeah, there's some other constraints that I'm not remembering. But you can't just do this for like arbitrary functions. There are constraints. Other questions? Okay, let's get back to the linear RNN then. I'll just note that we can parallelize these tree operations on different processors. So can we make this work for a linear RNN? RNN. Okay, so that means instead of the cumulative sum, we want to compute the following. H sub t equals a h t minus 1 plus b c t. So it is more complicated to compute this in the framework of this parallel scan. But I'll just show you the implementation that was put forth in that 2018 paper on parallelizing RNNs. We won't go into the actual details of how they came up with this, but once you see it, it'll make sense. So instead of having just one entry at each node, the first thing we're going to do is have two different entries. So we'll be considering a tuple like A, B at each node. So we're basically going to be computing two different functions at each node. So this is the operation that they propose. So given a pair of tuples, so this represents like how do we merge this node and this node to get this, the parent node. That's what we're interested in. So if we have two of these tuples, they define this operation, this new operation that computes the following. So the first element of this resulting tuple is the product of A prime and A. And the second element of the tuple is A prime B plus B. So if you look at these, you can kind of see the relationship between these and the unrolling of the linear RNN that we discussed before. So in particular, this part of the tuple, the first element is going to store the matrix powers of the A matrix. So we need to get all of the, A squared, A cubed, A to the fourth, and so on. So we're going to compute those as we proceed up the tree. And then this one looks more like the actual hidden state that we want to compute, right? So we're going to use this to compute either the hidden state itself or values that will be useful in computing the hidden state. But importantly, we're trying to do two things at once at each node. We're going to keep track of our matrix powers, which just to emphasize, we noted up here, right? It's part of the equation for the linear RNN. Okay, so now let's try and expand this and see what we get. And I'm not going to go over all of the details, but this is just a toy example. So let's say we are trying to recover this right here. This is our goal. How can we do this using this new operation here that we have just introduced? All right. Yeah. Yes. What do you mean? Oh, you mean over here? Oh, I must have, I think this is supposed to be B, let me just see the, yeah, this is supposed to be B prime here. Okay. Sorry about that. All right, so let's take a look at our inputs to this. Now, we have two different inputs, remember, we have a tuple. So I'll try and write a little smaller. Our initial inputs will look like this. So this is one input, this is another input, this is yet another input, and this is our final input. So note that the first element is always this A matrix. We're trying to accumulate these powers of the A matrix. The second one is B times the current word embedding at that position, right? Which we know is part of any of these hidden states computations. So now let's apply our rule to this node here. So the first element here, we get A squared. And the second element, we get A, B, C, O plus BC1, right? So that's good. And then here we get A squared again, and we get A, B, C2 plus BC3. So note that this is not the hidden state of any time step, right? It's part of the hidden state, but we will need to do the down sweep like we did in the cumulative sum in order to get this the hidden state for those terms here. So I'm only going to talk about the up sweep here, and you know, the details of the down sweep are oops, just trying to get some more space. All right, this is going to be split into 2 pages. Actually, maybe I'll just move this down a bit so I can write the final layer here. The new page. All right. So now let's do the second level of the tree, where the first element here will be A to the 4th, right? We're just going to multiply these two things together. And the second one is going to be A cubed BC0 plus A squared BC1 plus A BC2 plus BC3. So just like in the cumulative sum case, the root node here now contains the final hidden state of the, like in this case, I guess the third time step, right? But we don't yet have H sub 2, we do have H sub 1 here, but we'll need to do a down sweep to get the hidden states of all of the positions. But just like in the cumulative sum, you can see how now all of these operations can be done in parallel, right? And so what has happened is that people have written CUDA kernels to do these kinds of scans very efficiently on the GPU, which now allows us to scale these kinds of recurrent models to very large and deep models that you can train on a lot of data. And there are a couple papers now that have trained variants of these models on next token prediction, so language models. There's a Mamba checkpoint that has, I think, 3 billion parameters trained on about 600 million tokens. So obviously not as big as you know, like a 70 billion parameter model, but still kind of respectable, and it shows roughly competitive performance with transformers of the same size and the same amount of data. So there are many modifications of this general linear recurrent unit that people have proposed. Most of them are trying to make the matrices here, this A, B, C, D matrices, more input dependent. So as of now, each layer just has the A, B, C, and D matrices. There's no concept of like doing something like attention to get different parts of the input sequence into your hidden state. And if you're just bound by a fixed transition matrix here, your model is not going to be able to do things like in-context learning and all of these other things that transformer models can do. So a lot of the work that has gone into this newer class of models is trying to make this formulation more complicated, but still retaining the ability to parallelize all of the computations through a scan in this way. Okay, so any questions on this? Yeah.
I think even now the bottleneck issue and like the total property like with RNNs, like because of branching gradient,
Yeah.
capture long form particles. That still persists. So if you scale it up to say 3 GP per second and reduce it to completely.
Yeah, it's a good point. So we've focused a lot on how we can parallelize this, but at the end of the day, we are still representing the entire context with a fixed width vector, right? And we can make that arbitrarily deep, and maybe we have different vectors at each layer, but still, we are not explicitly doing attention over the long sequence, and we will have all the limitations of RNNs. So there have been some modifications made to these to similar to how RNNs themselves were modified using gates to get things like LSTMs and GRUs. We'll look at one example in a bit in the Griffin paper that proposes like a kind of gated linear recurrent unit. But yeah, people are thinking of these issues. There was a paper in about 2018 that showed that at the same scale, RNNs and transformers are kind of competitive. And also the newer class of state space models that Mamba is based on have shown competitive performance with transformers on this benchmark called, I think it's a long range arena or something like that, where it's not text-based tasks, but they have a bunch of synthetic tasks that require storing and reasoning over information from a long time ago. And modifications of these kinds of architectures can handle those problems just as well as transformers. But it's not clear how well those results scale over to, like text-based task, instruction tuning, RLHF, like that kind of reasoning that we know transformers can do. So it's a very new area of research. Hopefully things progress in this way, but it's also a little unclear if this is the way that we should go to replace transformers. Other questions? Okay, so in the remainder of the lecture, I wanted to just show you this paper from DeepMind that came out recently proposing two different architectures. One of them is called Griffin, and the other one is called Hawk. Thanks for being a great teacher. Thank you. That's so nice. All right, so let me just delete this iPad thing. And go to the display capture. All right. So this paper was released at the end of February by DeepMind. You can see by the title that it's kind of a hybrid type of model. So it has gated linear recurrences, exactly what we just saw, and local attention. So local attention is a variant of self-attention where you restrict the window size of the attention so that it can only look at, say, the last 1,000 words or something like that. In this way, local attention is not quadratic in the sequence length because you're always computing it over just a fixed number of tokens. But local attention by itself is insufficient to get all the properties that we want out of something like a recurrent neural network, which has this global memory state that, although it's a bottleneck, it could be used in conjunction with local attention to get like fine-grained modeling of the nearby tokens, but also global memory of the entire sequence through the recurrent mechanism. So that's the idea. I think a Griffin is some sort of like hybrid mix of two creatures or something like that, so it makes sense why they named it that. But I wanted to show first the, so this is one that's quite interesting to show. This plot on the right is showing you how many tokens you can decode per second. So it's a measure of the inference speed. And MQA is this multi-query attention. It's like a simplified version of the attention that we see in transformers. Griffin is their hybrid model that has both this attention as well as the recurrent layer. And Hawk has no attention at all, so it's just purely a stack of these linear recurrent units plus feed-forward layers. So this alone tells you the power of these recurrent models, right? At inference time, with 4,096 tokens decoded, they're 15 times faster than of attention-based variants, right? So this is one motivation for exploring these kinds of models. Obviously, there have been many developments to make transformers faster at inference time. We talked about maybe distilling a big model into a smaller one so it's faster. There are other approaches that we haven't talked about, such as speculative decoding, where you use a small model to decode like very obvious tokens and use the large model only on predictions where you might need the power of that model. But those are kind of hacky, right? And ideally, our model itself would be very fast. The same model that we trained would be fast at decoding time as well. They also show in this paper that these hybrid models and their recurrent-only model exhibit similar scaling laws to the ones that we've observed in transformer models. They also exhibit in-context learning ability, which is what we all care about these days, right? The ability to learn a new task from demonstrations, follow instructions, things like that. So let's just take a quick look at the linear block that, the recurrent block that they have here. So this is their recurrent block where first you can see that they compute these intermediate terms that have no dependence on the previous hidden state. So you have x sub t, the current input, let's say the token embedding at that position, and you have another like gate here with this, basically just two feed-forward layers. So you can think of these as kind of similar to how we computed the query key value vectors in a transformer, right? Just through feed-forward layer. These can be done completely in parallel. Now you have the hidden state, which again is has no nonlinearity surrounding it. So we have some sort of linear interpolation here. Some sort of interpolation between the previous hidden state and a function of these two projections that we get from the current input token. So this part of the term, it looks complicated, but there is no dependence on the previous hidden state in this term. So the general idea is that with respect to the previous hidden state, we have a very simple transition, but with regard to the current input, we have something very, very complicated and nonlinear. We can stack like more feed-forward layers here, or stack these blocks. But the critical thing is that this has to be able to be implemented as in one of these scans or as a convolution operation. So you can't get too fancy with the actual update equation involving the previous hidden state. Okay, so they also have some very strong results in this paper. So again, this is their transformer baseline. Hawk is using only recurrent blocks, and Griffin has some recurrent blocks and some local attention blocks. Again, local attention only allowing you to do self-attention over a small part of this sequence. All right, so let me go down to the results here. So here we see a couple different models. The ones on the top here are using different model sizes and different data sets, so we can't really compare the results from this paper to the ones up here, but it gives us at least a rough guide of how these other models are doing. So again, Mamba is kind of like similar in nature to this Hawk model in that they're both based on variants of this linear recurrence. And Llama 2 we know is a transformer. These are their transformer baselines and their Hawk and Griffin models with different parameter sizes. So you see that they train all of these models for 300 billion tokens. So they have a couple different data sets that they're evaluating on here. MMLU is probably the most popular one nowadays for looking at language models. It's basically just testing instruction following ability on many different types of instructions. So we see Mamba is about 26, and Llama 2 has the best results on this benchmark of all these models in the table. However, Llama 2 is also trained on way more data than any of these, so it's very hard to tell. So let's look at their Hawk model first, which has no attention. It's just these recurrence blocks, linear recurrent blocks. We see that on this MMLU benchmark, you are getting better performance as you scale up the model size, which is also something we observe in transformers. It is the desirable thing to see, right? As we get bigger models, the model is capable of learning more from the same data. If you look at Griffin, which is the combination of the two, we see that at a 14 billion parameter model, it's getting pretty good performance here. I mean, it's very hard to compare to this like Llama 2 checkpoint. You know, the number of tokens is different, but I don't know why they decided to choose 14B instead of 13B. The data sources are also probably very different, but you know, it's approaching that level, which is definitely a good sign. And on average, it's actually better than all of these models, although again, you have to be a little skeptical about how they even chose the models that they decided to compare to in this paper. If they chose, say, Mistral, maybe it would be a lot better. Okay, and the other thing is that if you look at the 1B, 3B, 6B, this curve here, we see 28, 31, 38 on MMLU, and pretty much the same thing with the Griffin model as you scale up the number of parameters, which also suggests, you know, similar scaling behavior in terms of model size. So overall, it is quite promising that this kind of model can work. However, there were a lot of comments after this paper was released that, you know, because it was released by Google, Google doesn't publish, you know, if it were critical to the models that they're actually deploying, it's unlikely that they would publish this. So a lot of people are kind of speculating that, well, it might not work at scale, and that's why they decided to release it to the public. Who knows if that's true or not? But you know, their Gemini blog post says very clearly that they've trained a transformer model, not a Griffin model, right? So who knows what is happening under the hood? But I would say it's pretty clear that these models are currently not competitive with transformers at the cutting edge, and it's going to take some very high resource lab that's capable of training them on huge scale data sets like this at a sufficiently high parameter count to really see if they have any advantages over transformers other than like inference speed. So I don't know if that will happen, but it's clear that there is more desire now to move away from the transformer than there was, say, even last year. So we will see moving forward. Yeah, so I think that's all I wanted to say. Are there any questions from, yeah? Oh, that's a great point. Yeah, so of course there are no checkpoints here released and no code, which is quite common from the industry labs. So it's very hard to verify these things for sure. And that's an even bigger concern even when the models are released and they have papers that show the results of their model on various benchmarks. And if you try it out yourself, you might get very different performance. And this has happened quite a bit with like Llama and Mistral models. People cannot recover the performance that was originally reported in those reports. And that's because they didn't release the prompt that they used on many of these benchmarks. So that's another thing that people are actively discussing is if you build a benchmark, like a data set, say something like MMLU, should you also mandate that a specific prompt should be used for all of the examples in that benchmark? There's also now concerns that because we don't know what is in the data sets of these models, there's nothing stopping these companies from just adding all the benchmarks that exist into their training data. And there was recently a paper that showed that many of these organizations are explicitly doing this. There's a data set for math word problems, and I think Mistral reported a really good performance on this data set. So just last week, a group of researchers created a new test set for this data set that consisted of different word problems. The same reasoning and same style, just different problems. And they showed the gap in performance on their new test set versus the public one was huge for some models and very small for other models, which might suggest which companies are actually training on the test data and which ones aren't. But because we have no way to verify, it is the companies are incentivized to train on all public test sets, right? There's nothing stopping them. They get more funding this way. So yeah, it's kind of sad. And it does mean that for new benchmark data sets, we probably should not release them at all. Instead, there should be like one team of benchmark maintainers who take new models, run them over their data, and release the results. And the actual inputs and outputs of the benchmark should not be made available to anyone. That way, they cannot be contaminated. So it's kind of sad because it hurts development. Usually in machine learning, we have something that we can kind of iterate on and hill climb on, but maybe that's not the way to go moving forward. Okay, other questions? Let me check on YouTube. Are you planning to take any courses next semester? I hope not. I am not teaching any next semester, if that's what you meant. All right, so let's end here, and thanks for the fun semester. Thank you all for not cheating on your exams also. And good luck on the final projects. We will have them all graded before whenever the grading deadline is. So yeah, look forward to reading your reports.